So we will keep going on with last week. I think we stopped somewhere around RNN and LCMs. But basically we will be talking more into music generation, and soon you'll realize the recent progress about the more controversial Suno, Udio, but also some of the other music startups are doing it in a more ethical and more correct way to acquire the license training data to train these models. But you will see the progress basically. So people start from symbolic music generation, think about, can we just generate these notes by notes, started like 50 years ago, but now we have these deep learning model to see whether these deep learning model can do better. And then we will see we can actually generate audio directly, like waveform, spectrograms. And in the end, you will see nowadays how these models are actually using a mixture of all the things we will talk about. Um, so it will take, I guess, two more lectures until then. You'll see a lot of like recent models that's, just like 3 years ago, or even like the future model like 2 to 3 or 3 to 5 years ago get started, and now it's becoming used in real life. Cool. Project. I'll think about the project pitch, but originally planned on Wednesday, but maybe we should delay it for a week or so. Cool. I think I can grab the recap slides. Cool. So basically symbolic music generation, meaning that we want to generate musical notes rather than, just the sounds. It's different because, once you have the notes, the benefit is that you can actually use whatever, like keyboard, synths. And for me, it's more like, what people refer to generating music. It's like if you ask someone to compose, it's not like, you just started making some sounds. Rather, you want to know what's the core of those, pitch, those notes are going. Even though, nowadays, part of the modern music or computer music is sort of like trying to redefine what music is, but that's sort of like going back to the core of music and think about what are we generating essentially. So symbolic music generation, basically two sort of like paradigms, and it corresponds to actually sort of like the two big chunks of modern deep learning. One is like natural language modeling, processing. So think about like RNN, LSTMs, transformers. These are, technology behind ChatGPT and all the, text-based system basically. And image-based methodology, sort of like CV, computer graphics. You see a lot of like image generation models, video generation models. So we can actually treat sort of like music, like images, and we can generate those. And that's what we will look into today. But we started from, text-based one. There's some benefit, and we can actually reuse a lot of like NLP techniques. So, this is basically just doing this music language models. There are other models that's not doing, exactly this next word prediction. But this is sort of the fundamental or the most basic forms of that, given all the previous notes, what's the probability of the next note? And so you basically just want to figure it out, like given CCGGAA, what would be the next probable note? And what are some of those, less probable one? And so the key is to see how we can define this like music, machine readable music language, how we can represent music in a way that machines understand. So, we've gone through some of those example, ABC notation, MIDI notation. But one of the most basic one is ABC notation. We've seen like months ago, 2 months ago, I guess. When we just started, we look at, ChatGPT can actually generate music in ABC form notation. So that's not surprising because, ABC notation is sort of like trying to represent music as like text that we can understand. It's just letters. It's just coded in a specific way. But 10 years ago, 2015, when people started to look into how we can generate music, we actually started from, generating folk tunes, just, single monophonic melodies. So we are using these LSTM. So last week we talked a little bit about RNNs, likely too simple. But basically the idea is that, I guess, RNNs. Sometimes you will be confused about what's going on with RNNs, why it's so complicated. But the core of RNN is that we are storing some state or memory within that module in the middle. So these models are different from, typical layer by layer models where there's not essentially something that's being stored. There's no state. It's not stateful that, these models doesn't have a memory. So RNN has the ability through this loop, through this, here's my cursor, this internal loop. Basically, you can store some information that pass over time. So that's the memory, that's the state. But RNN is known to be very tricky to train because these memories serve two purposes at the same time. It has to be, directly influencing the output, but at the same time, it has to sort of like be storing some information. So LSTM is basically trying to disentangle these. Something about the outputs, we will keep it that way, but there's something we should be memorizing. So this is basically the design of LSTM. Sometimes it will get lost, to just look into what LSTM is doing. But, the core of LSTM is to disentangle long-term memory and short-term memory, where long-term memory is trying to, think about some of the long-term things that you should remember. But the short-term one are, immediately affecting your outputs at that particular timestamp. So the idea is, once we have an input, we look at our memory and see if we want to erase the stored memory. So think about, core progression. If your long-term memory module is thinking about what core we are in, and then you generate several nodes, and then once you reach the next measure, you have to think about, well, is it time to, update our current chord? So that's sort of the idea, there's something that's longer span, like chord progression, but there are nodes going on for several chord, for several beats for this chord, and then you update that chord to the next one. So think about this way, whether we should erase the store, sort of like chord progression, and now we move on to the next chord. So that's the first decision. And once you erase it, then you can update it. If you don't erase it, you can still update it, but it will change that weight. So basically these two modules is trying to see how you update that memory. So usually I think about, something like chorus, something like, I don't know, verse, chorus. So think about something larger structure than, very localized stuff. But finally, you still need to generate something and it's just the timestamp. So that's the short-term memory where you still use your input, but at the same time, you combine it with, the long-term memory. So, if you think about long-term memory as like core, that's like structure, then you should use both of them to generate your next output. So that's LCM. They have specific names, cell state, for gate, input gate, output gate, but these are just a way to disentangle long-term memories from short-term memories. Cool. That's kind of where we stop at. Any question on this? Cool. There's actually one thing I didn't talk about is the difference between word level and character level LSTMs. So in this fork tune, fork IMN, it's actually using this character level RNNs. So it's not being used intensively nowadays. It used to be a hot topic between like whether one is better than the other. So nowadays, if you know a little bit about some of the modern architecture, we have like tokenizer. So tokenizer is looking at the root and the prefix of a word, and those could have specific meanings. Say pseudocode, like pseudo and code. That's like there's some meaning by looking at sub-word level information. So it used to be a hot topic, but nowadays, if you are talking about RNNs, still modern day architecture, we have tokenizer before actually looking into these words. But anyway, the difference is that, word level RNN is just predicting word by word. Character level RNN is predicting character by character. So it's useful when there's no natural spaces. That's essentially what we have in ABC notation, where these nodes just going one by one without any natural spaces. Um, but nowadays, we don't look at these. Nowadays we see a lot of like token. That's what people all talk about, tokenizer. So essentially nowadays we have these word embedding models that break these words into sub-word chunks of reusable small chunk of letters combinations. So things are a little bit different nowadays, but it used to be, word versus character. But now we have sub-word units that's like tokens. That's not small as character, but it's not large as word. But you can definitely see the limitations of ABC notation. It's like very limited expressiveness, monophonic tunes only. So we also hint about this, a month ago. So basically we can use MIDI-like representation. So I won't go through it again, but I guess one of the key thing is that MIDI note, middle C is 60. That's all you need to infer all the other no number. And it's widely used in so many different software. Whenever you see some number representing pitch, 99% chance it's MIDI note. But basically, we can sort of like represent music using MIDI message. Usually we just look at note on, note off, and time shift. This is the way how MIDI represent music. So, you turn on the note and then you wait for some time and then you turn it off. That's essentially how MIDI internally is doing stuff. So it's more like a control protocol than, sort of like a representation or, like a music sheet, sheet music notation. It's more like a control protocol. And it's designed to be a control protocol when it just started. I think it's 1960-ish. So that's like almost several decades ago. But one thing nice about MIDI is that we can actually represent polyphonic music, even though it looks a little bit weird, where you might have like interweaving stuff going on, but at least, now you can do polyphonic music. So, you will start a note and then you jump to somewhere else. You start another pair of notes and then you jump somewhere else. You close that second group of notes and then you jump somewhere else. Now you finally close the first note. So, you start something, you have to handle note on, note off. But anyway, you can do polyphony music at the end. So this is like performance RNN, which is sort of like one of the breakthrough of deep learning based music generation, where this is the sort of like the first time we are able to generate expressive piano music. So this data set is pretty cool. It's the Yamaha ePiano competition data set, typically known as Maestro. But this is basically Yamaha as this clavier. I actually saw one at Costco yesterday. So Yamaha has like a disc clavier. So this is like Bassendorf. They also have that ability. So basically when you play, you can record sort of like MIDI, but it's not like a keyboard where you get the MIDI and then you synthesize later. This clavier and this piano is that you play it as if it's a real piano. Just that underlying there's some mechanical laser measurement system that use light to detect how you press these keys. So it's sort of like trying to store all the information, how you press all the keys and where you lift it very precisely so that they can sort of like reproduce the exact performance that you have. And so that's essentially how this Maestro data set is created. It's kind of like a brilliant idea. They basically just launched this competition and then ask people to come and there's like prizes, but you have to sign an agreement so that you will have the data being collected. But now these data will allow us to look into how performance work. And recently there's also a new study that's very hot topic recently. It's like there's a study that's showing that the pianist, the fine grand touch on the key, actually expert musicians can is able to tell the difference between those after touch. So anyway, there's so many things we could talk about it, but performance iron is one of the first model that can do that fine grain expressiveness. We can listen to some of the examples. Again, this is even though one of the breakthrough, but it's still early stage thing. It's on. Let's see. So one thing you can see here is that there's like set velocity events. So you actually handle the dynamics, but at the same time, look at, the time shift event. It's like n millisecond to 1 second. So there's a lot of, expressiveness inside it. It's rather than, very fixed grid, MIDI-like. Usually these examples are generated with some framing melody. So you sort of like give it a prompt and then it continues. So usually it started very good. And RNNs and LSTM are known to be sort of like very unstable whenever the model makes some mistake previously. So that's one of the downside of these models. Nowadays we have transformer is much more robust to, recent errors. But you can see a lot of these models after let it improvise for a while, it will start generating, off the scale. But anyway, this is a very cool start of how things work. And Google actually created a very cool demo on that, which is I think
Hi, I'm your programming. I'd have to experiment. You play cool to see people.
Is there anything where it's playing?
It's also fun to just mash the keyboard. The neural net tries to return something coherent from any input that you give it. I made all of the code open source, and the neural
Anyway, that's not the demo actually. But the idea is pretty simple. Is that, well, even though we only have this model that can just keep continuing generating stuff, but one thing that you can create this AI duet is that you can pretend what the user generated are something that the machine generated. So you sort of like pretend those are machine generated stuff, and then ask the machine to just keep continuing that prompt. So that's sort of create a fun AI duet sort of like algorithm where it's essentially just like a ChatGPT. So think about ChatGPT as the same. It's like trying to produce a response to the user's prompt, but basically it's just doing that next word prediction basically. So this AI duet is very cool. It's like one of the first time that now we can see some of the music generation models can actually be interactive in some sense, even though it's not technically interactive. Much more recently, music transformers, same data set, sort of almost the same representation, but now we are using transformer, and we can actually get a lot better, generated result. And it abruptly, but this is another example. So you can see that the chord structure, I feel like. one thing you might notice is that these music tend to be very intense and big, grand kind of, because this is like the data set. The data set is piano competition. So, typically those are, hard pieces and, very skillful pieces. This is another example. I believe it's generating continuation. Yeah. Sorry about that. Cool. So you likely get a sense that, of course, the first several notes it's not generated, but it sort of there's some like memorization going on. You can feel that, well, that's not in the prompt, but somehow the model just basically grabbed that motif exactly and put it there. So that's a bit weird. But other than that, the music kind of like flowed around, and at some point it sort of like forgot what's going on with the initial motif and sort of like drifting away. And actually, I think in the later part of that, it actually sort of like referring back to the original motif. So music transformer, we would talk about it, but it's like interestingly, there's more, long term thing going on. So, music transformer, almost the same representation as performance RNN, same data set, just that now we have much more sophisticated models that similar to the one that we're using for ChatGPT. Um, Transformer. Have you learned about Transformer yet? Okay, cool. Then life will be easier, I guess. Transformer is one of the model that's just like too big to break down at some point. And then once you break it down, and then once you assemble it back, and then you will be still wondering what's going on within this huge model. But anyway, the biggest idea of transformer is about the self-attention thing. So, we won't go into all the details, but sort of give you a hint why we are doing the self-attention mechanism is that, think about this, the same idea, a transformer is something, then, there are words that's more probable than others, then think about like a model that just look at these words sort of like equally. And it doesn't make much sense because some of these words are more important than others to determine the current words. So the idea of transformer is to learn what to attend from big data and to play, variable weights onto the previous context. So in this case, to determine what the next word is, transformer is likely much more important than the other words. But, the other words still carry some information, that it's not, it's singular, it's rather than, plural. But, most of the information will come from the word transformer. So that's essentially what transformer is doing. So the rest is just some animation to show you sort of like step by step the composition, demystifying what transformer is doing. Hey, um, so again, we are trying to predict what the next word is. So this, question mark here is the immediate next word that we are trying to see what that is. So for transformers, basically we break each of these words and we try to predict three things: query, key, and value. And we will use these three vectors to do all the thing we want. So as I said, transformer is trying to sort of like pay attention to different part of the inputs with different weights. So that's the key. So, the idea is that now we are generating the next word. We will use the immediate previous word as the query, and we want to try to prop to each different previous words, and those are the key. So, for example, we can have the key for A, and then we have the query for the second last word, immediate previous word, and we can see, try to see how much weight we should pay attention on this first word. And then we do the same thing. Basically, we now use the same query and we check it with the key. So you can imagine, sort of like in the perfect ideal world where we have these attention score, basically where sums to one, and hopefully they will reflect how much attention to attend to. But again, everything will be learned. At the beginning, the model has no idea which one to attend to more. But overall, through learning through the data, the model should be able to recognize that transformer is a much important word to determine what this next word is about. So once you have those attention score, which we will call sort of like a weighted sum of the inputs, now you basically just grab the value vector, and now you do a weighted sum over those. So now you are basically predicting the next word using a weighted sum compute dynamically onto all the previous words. So now you have a transformer is there for words, but now transformer will have a much more higher inference on the outputs. So that's essentially just what transformer is doing, this like self-attention mechanism. And all these things is just to have these model to go one by one, because at some point each of these will become the query when you want to generate the next immediate word. So you might ask why attention mechanism? So it actually started not from generating next word prediction. So the original transformer is actually for translation rather than nowadays we are using ChatGPT. So transformer, the original transformer is unlike this. The original transformer actually have an encoder and a decoder. This is just grabbing the decoder part. Nowadays, lots of the models we talk about is just decoder only model, but at the beginning, it's a encoder decoder model. So why encoder decoder model? Because initially this attention mechanism is trying to solve a question, a problem in translation, where in translation, we are thinking about, in this case, we are going from French to English. Then some of the case, in this case, zone, economic, European. So basically that's European economic area. So, different language will have a different ordering between words. So that's essentially how this attention mechanism was proposed initially. It's like, can we sort of like dynamically model this alignment between two different languages? And at the left, you can see that, they also apply it to generation. So this is like the FBI is chasing a criminal on the run. So this whole is like the model is generating. But the red one is like when we are generating the FBI, it looks at the, and then when we are generating the is, it's looking at FBI. So this is reasonable because there's no way you should look at the. You should look at the FBI, where you should want to see is singular or plural. Now chasing, it will look at both FBI and is. And now as if you're looking at then it will look in chasing. Now looking at criminal, then it will look at chasing is. So now you can see that, over the time when you're generating each single word, you are actually paying attention onto different things. So that's essentially, what this self-attention thing is talking about. When you're generating different words, you want to pay attention. That's different from other, and it should be dynamically determined based on the exact context that you have. So that's sort of the backbone of transformer. But more interesting, visualizing music self-attention. So this is the song that you just heard. But basically, you can see that this is like trying to visualize the musical self-attention. One thing I didn't talk about is that there are multiple attention hat. Likely, you might know a little bit about it, like multi-hat attention. Basically, there will be grouped attention that look at different components of the music. So we can look at this very cool animation where you can see how the So, you can actually see that it's sort of like attending to very interesting things. Of course, like the first note, usually you will see an attention to the immediate first note that sort of like set the whole key. And you also see that it attend to the immediate previous chords and the root note. So it's kind of interesting to see what these model is actually looking into. It look at the chords, it look at the patterns, the fragile patterns, the chords, but it also look at some of the relevant notes. So it's not paying attention to everything. It's selectively paying attention to some of the inputs. Any question on this? This is also like a engineering, I don't know, nightmare to actually plot this. So I guess one of the key idea of, I think this is itself, I remember it itself is a research paper about how to visualize this. But it's sort of like clever to see how you visualize these attention. It's a little bit different from words, right? You can like highlight these, but it's not obvious how you can do it in music. Cool. So yeah, I mean, like in this example particular, it attend to the first chord. It also attend to the current chord, especially the bass note, to see what the chord is, so that you will get the note right. But it also look at when you are doing these, fast grouping notes, it will look at the exact same patterns previously occurred. In this case, this part and this part has that fast moving chords. Cool. So, that's music self attention, which is pretty cool. That, sort of like hint you a little bit about why Transformer is in most case doing much better than LSTM, where these Transformer has the ability to look in the further past. In this case, the first note or the first chord, or the first chord that defined the key of this piece. Cool. So we'll just move on. But there's tons of things that's beyond solo music. We mainly just talk about single instrument music. There's a lot of things that you can actually do with multiple instruments. Typically, we will use MIDI program change message to sort of represent instrument. It's not ideal, but it's better than nothing. So, looking at MIDI program change, there's actually a bunch of different programs. Say, 1 to 8 are the pianos, and you see different types of piano. But at the same time, if you look at some of the MIDI program, it doesn't make much sense. There are like audio effects. There are like things that's sort of like undefined. But anyway, this is better than nothing. At least you get, the most basic ones. Most basic instruments should be included in this case. And that's essentially how we get some of the data, because otherwise we don't even know what that instrument is. Anyway, there's some other models that you can do, much more complex music than, just solo music. So in this case, we would just browse through some of the example, and mostly the idea is that data is different, and how do you get a good representation to represent music in multi-instrument. So in this case, this is a much larger data set, because Maestro only have piano, because that's how the e-piano competition is working. But they also look into classical archives, bit MIDI. So these contain multi-instrument music. So the representation is pretty cool. Basically, instrument and column, velocity, column, pitch. So in this case, now every single note becomes a super note, where you actually contain both the velocity and the instrument information. So this is like what they can generate. Cursor. So you can now actually generate drum and piano. There's a bass. Basically, this doesn't change anything about what you're doing. You're essentially still doing transformer. You're still doing next word prediction. Now the question is like, how do you effectively and efficiently represent music in that format that the model can effectively learn that pattern. So this is one example, you see piano V72 G1. So, a piano playing G1 at velocity 72. And you have violin in another velocity, another pitch. There's also other examples, multi-track music machine. This is a little bit more complex representation, but this is essentially actually how MIDI is representing music. So where you have this huge chunk of multi-track, where you have like P start, track start, and then you have a bunch of things about that track. So within each track, there will be, what this track, the instrument is, what's the note density. This is useful for conditional generation. Now you have a bunch of bar. Within all these bars, there will be the actual note on, note off. Somehow it shows up. Yeah, so you will have a bunch of bars. And once you have all the bars within that track, then you go back and then close that track end, and then you start a new track. So, this allows us to do some of the interesting this is what the multi-track music machine can do. You can actually replace a track. So what just show is that this is the generated drum. And if you don't like it, you can just regenerate that track particularly. Now it's like generate to replace that drum track. Anyway, the idea of this, this representation, it actually has one benefit that's, make it much more relevant in the so-called, when you want to add a new track to existing composition. So if you look at these kind of representation, then it's not so obvious how you can now, think about once we have this composition, how do we add like a new guitar or say viola or cello onto this composition? It's not so obvious because, everything is twined, all the notes are interweaving patterns between different instruments. So, in multi-track music machine, because, each track is generated one by one. You generate one track and then the next track and then the next track. So it's much easier that you can actually just append a new track and you can set what instrument you want so that you have prompt the model to generate that particular track. So this is, there are some benefits. There's always trade-off between all these different representation. Some of the representation generate better music because everything is twined, but some of these models are better at adding a new track or recompose a specific track. There's also this multi-track music transformer thing. The representation is again a little different. So you have like beat, position, pitch, duration, and instrument. So we can listen to some of the examples of the generated music. This is like classical, sort of like orchestra. Cool. So I have a question for you. Why don't we need time shift in this case? Any thoughts? Position? Yep. So, there's also difference between these representations. So previously we talked about, you start a note and then you move and then you close the note, that kind of representation. But there's also other representation where we basically just specifically say beat one, the second part of that, and then B2, B3, So this kind of another kind of representation where you specifically just specify where exactly that beat is. And these beat information is sort of like similar to when you are generating text, where you have the positional encoding. So you can think about there's a tons of recent research discussing this effects where people find that in transformer, when you are generating text, the positional encoding is very important. Otherwise, the model see all those words the same, right? So you want to have positional encoding so that this is the immediate last one. That's the second last. That's like far away. That's the first word of this document. But in music, it's a little bit different. It's like, well, how do you even know like three notes before in an orchestra music? It's kind of different from three notes before in the folk tune, where three notes before for a folk tune could be the last measure, but in orchestra music, three notes before, likely you're still at the same chords. That's a huge chords. So these kind of, temporal encoding, you can actually try to incorporate these beat and positional information into your model so that your model are actually, because once again, when you are doing self-attention, you are basically using the data itself to dynamically learn the dependency between different um, words and tokens. So in this case, if you have beat, position, pitch, duration, instrument, all these information embedded in your representation, then when you are generating the next note, you are essentially looking at all the previous notes with the full understanding of where these notes are, what are their instruments, and then you dynamically determine which one you should look at. So there's tons of different kind of representation. Is a very active field actually. But still, we still haven't figured out what's the best. And there's always some trade-offs between these representations, and there's not one thing fits all solution. It's a little different from, it's sort of like similar to how people looking at different tokenization approach in NLP. But in NLP, mostly you are thinking about sequential language generation. There's other cases, but mostly sequential. We can also do drums. Channel 10 in MIDI is reserved for drums. So you can actually generate drums. We just saw like an example in MuseNet and music multi-track music machine. They both can generate drums, but you basically just need to treat drums a little bit different from other notes because drums has a specific encoding. So many different representation for music generation. We won't go into details, but there's actually, because it's too tricky, so there's actually a package to handle all these. But just think about it like tokenization, thinking about treating different language, how you should use different encoding for different languages. So for music generation, how do you represent these music actually has an inherent inductive bias onto the music that you would generate. There's a bunch of like symbolic music data set. We sort of look at some of those. We look at the folk song, Baccarel, likely what those are. Lock MIDI, what the MMM is trained on. Maestro is the piano music with expressiveness. But there's a tons. So if you want to play with those, they're available. Cool. So I guess that's it for the language-based music generation part. We basically just keep moving on and look at some of the other case where you can actually do expressiveness by encoding additional, time shift events in real time rather than, in symbolic music, non-expressive symbolic music where you don't have those expressiveness. And you should also encode the velocity. And we also look at, music transformer, basically swapping the performance, the RNN part of performance RNN into a transformer. And we look at, these transformer, how it actually attend to some of the musically meaningful components. Cool. Any question on all these? Is it sort of like expected how people treat music? Yeah, I sometimes feel like it's a little bit I don't know, ignorant treating music this way, but at the same time, it's like the same as languages. It's like there's so many knowledge embedded in language, but somehow we are just looking at, this next word prediction. And ironically, it's also working to some extent, which made me sometimes like just rethink about what, you know, knowledge is. It's like there are like superficial words generated by these models. Are these models actually doing the right thing? Who knows? Cool. And next we will talk about some of the, piano roll based music generation where, this is like a cool visualization of the early times when we are generating these GN. So GN is known to, you know, sort of like the start of this Gen AI era, for the image part, I mean. But, you see, at the beginning, it will be purely noise, and then you started to grab some of the pitch range, and then at the end, it generates some chord patterns, drum patterns, bass. It's just cool. We'll learn about it. But basically, piano roll based music generation is trying to treat music as more image-like representation. Let me see where my slides are. Shall we change our time for a project pitch? It was originally on Wednesday, but now I feel like it might be too rushed.
I thought it was pitches.
Oh, November 5th? Oh, okay, cool, cool. Next Wednesday. Oh, okay. Then let's keep it that day. Yeah, and feel free to book a time to talk about it. I think I accidentally removed the project pitch time. Oh, November 5th. 5th. Okay, let's do it that day. So next Wednesday. I will add more office hour time so that we can chat on that. So that should be easier. And if you couldn't find a time, just send me an email. Then we can schedule a time. Cool. Open-ended, so whatever you want to work on, and I will likely just like you give me like an idea. I will send you some stuff to look into and hopefully can figure out an interesting question to work on. Cool. Yeah. And it could be any topic. I mean, some of the topic we haven't reached yet. I mean, like some of the processing, editing, recommendation thing. We haven't reached that yet, but you can also work on it. I mean, at some point, or the slides for last year is still there. So you can definitely check into those. So it's more broader than you expect. There's so many different things you can think about as potential project topic. Yeah, some of the examples last this winter semester is like, people look at image to music generation. Like think about like can you use like an image to describe the emotion that you want to generate in music. So the idea would not be, you're training a totally new model, but more like, can you prompt ChatGPT in a way so that it generate a description for that image that can later be used to prompt another music generation model. There's also a study about, human versus AI, like sort of like a Turing test on the AI mastering things. And now we also have, Moises has like AI Studio. So you can also look into, some of these technology, whether they are just evaluate how good they are, or do humans have like a bias towards AI music generated? If you can sort of like do a like social experiment where you know intentionally confuse them about whether this is AI or human composed music, then to compare their difference. But other examples, pitch detection, and then you can do hum to search. You can even do there's also a group trying to build a model that can just sing and hum into it and use pitch detection and use that pitch to condition a music generation model. So you can sort of like just hum about a melody, and then it can suddenly turn it into a full composition with your pitch, you are humming as the conditioning, as the main melody, basically. So there's tons of things you can do. So feel free to explore. And book a time to chat. I guess that's more efficient. Cool. Guess we could just keep moving on. So we talk a lot about the text-based one, then now we are jumping into the image one. So you might be able to imagine that we might be talking about GNs, VAEs, diffusion models. So all sort of these big new deep generated models. So before that, we could just look into what piano roll is. I think we've touched on this early in the first several lectures. So basically, you likely know what it is. It's just this, scrolling things where it will trigger those, keys to the hammers to hit the keys on the piano, on these piano player pianos. So we will skip this. But basically, piano representation is sort of like, once we know about spectrograms, now you see how similar they are. So on the x-axis, there will be the time, and y-axis will be the pitch. So the idea is now, it's just that how can we generate music in this format? So sometimes you will also have brightness to represent the MIDI velocity, but that's optional. You can also do expressive timing or without expressive timing, so they will have a little bit different look. But basically, the idea why we are using piano rolls, just as in music language modeling, is that you're trying to do the next word prediction. But now piano roll representation has another feature where you have these reusable pattern detectors. And so the time when we were talking about this is when we were introducing CNNs. So you will see a lot of CNNs in these piano roll-based music generation models, where these convolutional neural network is basically learning all about these reusable pattern detectors, where these penguin detector can be reused, the beak detector can be reused, but at the same time, all these features can be reused across different regions, different part of the images. So why piano roll? So the idea is that, by just looking at these, you can definitely see that there's something going on. That's very like, what CNN is looking for. So these are basically, filters. So think about C major, C minor. Could it be sort of like a filter in a CNN where basically C major, if you move it a semitone above, C sharp, a semitone above, then, D major. So there's like these translational invariance going on piano roll, and you can also move it temporally. So the idea of using piano roll is that basically you can just visually look at the piano rolls and you can see a lot of these, reusable patterns. So, many musical patterns like melodies, chords, scales, and arpeggios are translational invariant in its nature, both in the temporal and pitch axis. So the first thing we will talk about is this MuScan thing. So basically it's like a GN for piano rolls. Have you learned about GNs? No? Cool. Then there will be something new. GN is more a CV, CG thing rather than the transformer for NLP. So I guess that's the two paradigms I was talking about. So there's one paradigm talking about, how you generate these sequential things. But for image, for, graphics, we are more thinking about parallelly generating a picture. There's no sequential relationship between these pixels, technically. But anyway, for music, we do have temporal, but it's like, well, we can treat it as image in the first place. So GNs, as we will see later, is that, this is sort of like when it gets started, is that one thing you will see, this is not actually step 0, it's actually step 1. So in step 1, that immediately base track just realized that, well, base is like usually very sparse. So over the time, these model will just learn to improve over time. and it will start to notice that bass and drums is sort of different from guitar and strings and piano, where guitar, strings, and piano are more, polyphonic, more chords, more, horizontal things. But for drums, it will be very dot-like. So if you can sort of like see, these dots are basically, hi-hat, the hi-hat that, and then there's bass, there's snare in the middle, and there's drums that's, usually happen on the beat. So you can see those patterns. So this is basically what GN is doing. So we will talk a little about GNs now. Cool. This is finally something new. Cool. So one thing that we should talk about is the difference between discriminative and generated models. So, nowadays it's very hard to sort of like differentiate between them. But basically, discriminated model is just looking at the boundaries. We don't really care what these distributions are. I just want to know where are the boundaries. So you are just drawing a line, I don't know, drawing like a highway, I don't know. But generated models are different. These models are trying to model the underlying distribution of these, two different distributions. So in this case, generated models still can be used to do this discrimination, discriminative task, where once you know the probability of these two distributions, you can still, draw a line between them. But the idea is that generated models try to learn the underlying distributions. So the whole idea of GNs, or generative adversarial networks, is about, can we generate data from in the data distribution that we are interested in about. So it's actually called the deep latent variable models. The mathematical foundation is very complex, but basically in this case, we can simplify it a bit. The idea is that, well, it's very hard to just randomly generate a random image. But what if we have like a random, noise image, and we want to see how we can turn this randomized image into a real image? So now the question is different. Rather than you are generating something totally from scratch directly to the image, now we are trying to map a random distribution to a data distribution. So that's the idea. We have a randomized, input, like a random image, and our goal is trying to fix this randomness all the way until we get the real image. So that's essentially what these deep latent models is trying to do. We want to generate new samples from the data distribution, but we don't directly jump to that. We sample something from the random distribution, and we try to find a mapping between them. So this is very challenging to think about it. Like, how do you define whether you are doing it good? So, when you have like, like some random distribution, now you go through some neural network, it would generate a bunch of random images, likely when you get started. So maybe it's like this shape, and your target, distribution look like this. Then the question would be, how do you measure their difference? So there's essentially no way to do this, because think about, these are images. So you have a bunch of noisy image, you have a bunch of, real image. How do you compute how far away they are? So the beginning of all these GNNs idea is sort of like thinking about how we can do this. So the idea they come up with is like, well, there's just no easy way to measure the difference from samples, but what about we just use another neural network to do it, to see whether these two distributions are close enough, the one you generated and the one that you have. So that's essentially what generative adversarial network is doing. So think about this way. You have a bunch of real examples. So a bunch of real images, a bunch of, songs that you like. And now you have a weird generator that, forget about what it's doing, but basically, you have some random seed number, random number, and you want to generate a fake image or fake music that you can do. And now the idea is that, well, we don't know how these fake samples are close to real samples or not. So we introduce another model called discriminator, where this discriminator is just to tell whether each sample is real or fake. So the idea is that, well, the discriminator aims to tell the fake samples from real samples, but at the same time, generator aims to make the fake samples indistinguishable from from the real samples for the discriminator. So that's where this adversary comes in, where generating trying to fool discriminator, but at the same time, discriminator trying to tell them apart. So that's the essential fundamental things about generative adversarial networks. And, this can actually be trained, just that discriminator has a different loss from the generator. So if you look at this loss function, you can, it look weird, but basically, if you want to minimize this term, you want discriminator X to be higher. That basically means that, well, discriminator wants to tell the real samples as real. So X should be, discriminator X should be 1. That's, that's doing right prediction. And at the same time, you want this generator X, Z, to be lower. So basically, discriminator is that, well, I want to classify X as real. I want to classify Gen Z, that's Gen Z. That's weird. But Gen Z, that's basically your fake samples as lower. Unfortunately, that's Gen Z. Anyway, on the other hand, generator has a different loss. Basically, what it's doing is that Gen Z has to be higher. So that's essentially what it's doing. And you can see that these two, Gen Z are going toward the different direction, where generator tried to push that into making these image look real, but discriminator want to classify them as fake. So that's essentially what these generative adversarial networks is doing. So, this discriminator will actually be discarded once you train it. So it will be drop it basically. So once you have trained these models, you can basically just grab some random noise and generate the fake examples. That might be a little bit too abstract. So here are some, real examples where, this is like deep convolutional GNNs. So when GNNs first proposed is just linear models, which is a little bit hard to tell what is going. But this is sort of like another breakthrough in GNNs where, the first time we can generate these. No, these are reals. We will see the generated ones. But basically, you grab a bunch of real. This is the LSUN bedroom data sets, which is famous because, this is a lot of like bedroom, and you try to generate these bedroom basically. So now the generator will be a bunch of, convolutional layer, go from like a random vectors and all the way you just reshape it using convolutional neural network. This is called transposed convolutional network. So convolutional network can be used to downsample an image, but it can also use to upsample an image. So, think about the filter. If you have a smaller like 2x2 things, but you can add that, filter and then just pass them 4 times, then now you actually get the bigger images. So that's sort of like the idea behind transposed convolutional neural network, where you can actually use those filter to grow the size of your images. So, growing convolution resolution that's used in transposed convolutional layers. So these are some of the models, some of the image that they generate. And so this is actually the first time that people just realize, oh, we are entering this new era of generating something that potentially could be real. And, that sort of like opens up the next 10 years of all these generative AI for images and video generation. But, the idea is that at the beginning, these just look really, really bad. And the discriminator will be so doing easy job where, these are so obviously fake and the real ones are obviously real. So the generator will improve until the time where the discriminator couldn't tell whether this is real or fake. So it's sort of like playing this game theory things where, generator and discriminator, and you will always have to sort of like balance their strengths. Usually discriminator is much easier task than the generator. So think about, look at these, as human, it's like so obvious these are unreal. But at the same time, if you don't provide useful information or for the generator to learn, if you just say, yeah, these are obviously fake, then it's not that useful. So the whole idea of GNs, a lot of research is about how do you provide the meaningful constructive feedback from the discriminator to the generator. So basically, this is GNs. So what we can do with generating music using GNs, well, we can just basically grab it. So the first thing we try is actually generating melodies. So this is the first model that actually use GNs to generate music. So as we talk about, we have piano roll. So we can actually just use piano roll to represent melodies. So it will be a little bit kind of wasting space, but it works. So these are the piano roll of a melody. It's basically taking 1 per 128 possibility. So it's not the best way to use this matrix. Even though in this case we only limited in 3 octaves, 1 octave above and 1 octave below, but it's still very low memory usage. But anyway, you would just go from noise all the way to generate this measure. And the goal of this discriminator is that you take a bunch of real melody as measure, and then you look at the one that generated by your models and see whether they are real or not. So one thing about MIDI-NET is that it actually do something more, is that it can actually add a conditional CNNs where this part is sort of like a U-net. It's a little bit hard to see, but the lowest part you can actually connect to this. The up level part you can connect to the last one. So it's sort of like a U-net things. So this conditional CNN is actually getting the previous measure. So this is how MIDI-NET just like, well, this is like the beginning of like trying to use GN to generate music. But given the previous measure, can we generate the next measure? And for the discriminator models, it's looking at the pair of previous measure and this measure to think about, well, is this measure a reasonable continuation of that previous measure? So that's one thing important about conditional GNs, where you want to have that previous measure also as input to your discriminator. Because otherwise, this discriminator will not look at the previous measure because that's not important for it to see if it's real. Cool. These are some of the generated music. You can actually also add co-progression as conditional. Eight years ago. Not exactly. So the progression is actually already given. So the model is just trying to generate a melody given that co-progression. So not the best, but kind of work to some extent. So we can actually look at the generation per epoch. So this is when it first the first epoch. So now we actually turned it the other way, which is really weird. But anyway, now this is like a piano roll turn 90-degree basically. But you can see that, over the time it generate more interesting melodies. At the beginning is everything is two-buried, and in this case there are also multiple notes possible. But over the time, when you train the model long enough, now this is the last epoch. Now you can see that even though the model still sometimes struggle about which note to use, but anyway, it's generate some melodies. And these are the ground truths. So you can see that, it's not too bad and it's doing something. I guess we are running out of time, but next we will basically look into how we can actually generate multi-track music. So this is the one I can play you some. example. So you can basically extend the same idea to generate multi-track music. It's like 7 years ago. Cool. So this is like 7, 8 years ago, and now we have Suno. So think about that progress. How quick this field work.